All right, so we're going to talk about rational functions, and we're going to start the discussion. We're going to look at kind of some of the precursor stuff to help us in order to be able to graph these polynomial functions. So if it's a rational function, what that means is that we are talking about one polynomial being divided by another polynomial. So it's going to be written as a ratio, so polynomial P over polynomial Q, right? And what we're going to focus our attention on is the denominator, because as we know, something we have been talking about all along, right? I made a note down here. We've considered and solved for this situation since day one of class. If we get 0 in the denominator, we know that causes a problem. And I haven't told you that or reminded you of what it is, but basically that is where we end up having a vertical asymptote. That is what's referred to as a point of discontinuity. And there are two types, so we're going to get into that in just a second. So the other reminder here, if you notice, kind of a property or something that you need to be aware of, is the domain of rational functions. So we have polynomial over polynomial. The domain is going to be all real numbers, except obviously when that denominator is equal to 0. So more on that shortly. So two different types of what we refer to as points of discontinuity. And there are two types. So one point of discontinuity is referred to as a vertical asymptote, and that's the main thing that we'll discuss. It's also possible to have holes in the graph. And we'll look at how we find and discover which is what when we have each type. Okay? All right, so the process that we're going to use, kind of the steps of the process, when you see examples of polynomials over polynomials, these rational functions, to help us with graphing these, this means we're not going to have our graphing calculator available. To help us with graphing these, we're going to factor first. We've got to factor top and bottom, numerator and denominator. And then we have to consider what's going on there. When we factor the numerator and the denominator, if, I'm going to jump down to number 4, if there is a common factor in both the numerator and the denominator, then that is what's referred to as a hole in the graph. And then once we have looked for any factors and we've divided out any factors that there might be, then we look at our reduced polynomial, our reduced rational polynomial function. And then we look at whatever's going to solve and make that equal to 0, because that is where we will have our vertical asymptotes. So if there's still factors left in the denominator after we have divided out any factors, then that's where our vertical asymptotes are. So two types of points of discontinuity, vertical asymptotes, holes. We're going to look for holes first because we're going to look for common factors. We're going to divide those out. And then we're going to look at what's left over, and then that's going to give us where our vertical asymptotes are. So let me show you some examples of what I mean by that. So the directions will probably say something like find points of discontinuity, describe them as either vertical asymptotes or holes. So the process to begin with is exactly the same because we are going to have to factor. So our numerator is already factored, but our denominator we've got to factor, and that's going to factor into x plus 3 and x minus 1. So that's our function there. We do not have anything, there's no common factors, so we do not have any holes. But what we do have to do is figure out where our vertical asymptotes are, and that would mean that we set our x plus 3 equal to 0 and get that x equals negative 3. And then x minus 1 equals 0, and we get that x equals 1. So our vertical asymptotes are at x equals 3, x equals negative 3, and positive 1. Okay, so there are 2 points of discontinuity on this graph. Let's factor this next one. So this one factors into x minus 2 and x plus 3 times x minus 2 in our denominator. So what we notice is that we have a common factor of this x minus 2. So that's telling us that we have a whole at x equals 2. But then our simplified, if we divide that out, then we are left with this particular polynomial function. And we need to look and consider if there are any other points of discontinuity. And in this case, because we still have this factor down here of x plus 3, we know then we have a vertical asymptote at x equals negative 3. All right, and then last one here, if we factor this numerator, we've got x plus 1 and x minus 1. And in our denominator, we have x plus 1. So once again, we see that we have common factor here of x plus 1 in numerator and denominator. So that's going to divide out. But before we've let that disappear completely, we do need to think about the fact that that means that x plus 1, we set that equal to 0, and we say that there is a whole at x equals negative 1. But that divides out, and we are left with just this single function that's just a line, isn't it? So there's nothing in the denominator to give us any other types of points of discontinuity. So it's just we only have a whole on that particular graph, and then we would have this line that we would have to graph and then draw the hole in there. So we'll get to the graphing part day 2 of this. All right, so along those same lines, besides talking about the holes and the vertical asymptotes, the other way these questions might be worded is that they basically just ask, state what the domain is, or state what the restrictions on the domain would be. So the directions for here would be something about the domain or restrictions on the domain. And so we're still focusing our attention then on what's going on in our denominator. But then if it's asking to state the domain, then we're going to use our interval notation to write out our final answer. So we've got some more factoring to do. So to factor that numerator, we're going to be x plus 2 and x minus 2. In the denominator, that factors into 3x plus 4 and then x minus 1. So if you notice, there are no holes, no common factors in top and bottom. But we do definitely have vertical asymptotes. And our vertical asymptotes are going to be where 3x plus 4 is equal to 0 and x minus 1 is equal to 0. So basically, if that's where the vertical asymptotes are, that's where our restrictions are. So remember, this is when we go back and we say, okay, x cannot be negative 4/3, or basically that, that's where it's causing problems, basically, right? So at x equals negative 4/3, at x equals 1, we've got vertical asymptotes. We know that now. So to state our domain for this particular set, we would say it's going from negative infinity to negative 4/3, from negative 4/3, to 1, and then from 1 up to positive infinity. Okay, so that's how we would state if we said the domain. So what I'm talking about when I say if it just says state the restrictions are what I was saying earlier. X cannot be equal to negative 4/3 or positive 1. So depending on how the question is worded, that's what you're going to be giving me in terms of the answer. All right, let's look at the next example here. For this one, when we factor, this one's a little bit easier to factor. Right? We get x plus 5 and x minus 5. no common factors in numerator and denominator, so there are no holes again. So we see, if we set each of those factors equal to 0, we see that we get that x is equal to -5, x is equal to +5. That's where our vertical asymptotes are, is at those particular values. So for our domain, we would say that our domain is from -infinity to -5, from -5 to 5, and then from 5 up to +infinity. So that's how we would state the domain. If I asked you to just state restrictions, then we are going to say that just that x cannot be equal to positive or -5. All right, last example of this type. And we're factoring x plus 5, x minus 5 in the numerator, and we have x minus 5 in the denominator. So what that tells us then is that we do have a hole at x is equal to 5. And that is a point of discontinuity also. So if we were to state the domain, we would say that we would be from -infinity to 5, and then from 5 up to +infinity. If we were just stating the restrictions, we would say x cannot be equal to 5. Okay, so onward. What we're looking at now is how we find those vertical asymptotes. We're going to practice strictly just looking for vertical asymptotes and holes a little bit, and then we're going to talk about how we find horizontal asymptotes, because that's going to be part of these rational functions as well. All right, so vertical asymptote, we know is that's when 0 is in the denominator, right? So the directions say find the vertical asymptotes if any of the graph. I'm going to add into that because along with that there may be holes. So we're going to add that to our list of what we're going to do here also. So add a little note and holes. All right, let's take a look at this one. I've zoomed in a little bit here just to make sure that you can see this. That numerator on that first function is a little bit trickier to factor because of the GCF. So I've already written out, if you factor out the common factor, you factor out the common factor of 2, then we're looking at that x squared minus x minus 12 to factor. Excuse me. So the numerator factors into that 2 times x minus 4 times x plus 3. Denominator, notice, is going to factor into x times x plus 3. So I do see that we have common factor. So that's telling us that we have a hole at x is equal to -3. But then to find our vertical asymptote, we're strictly going to focus on what would be left over in our denominator, which is strictly just that x. So that means that we have a vertical asymptote at x equals 0. And that's what they were asking for, is find the vertical asymptotes and holes for each particular function. So similar to what we did on that first page. All right, let me change colors here. Let's look at this next function. If we factor the denominator, numerator is already dealt with, but if we factor this denominator, we get that x plus 1 and x minus 1. No common factors, so there are no holes, but there are going to be 2 vertical asymptotes, and they're going to be at x is equal to -1 and x is equal to 1. And then lastly, let's take a look at this one. This is already factored for us. Definitely no common factors in numerator and denominator, so there are no holes. But if you notice, we have 3 different places where the denominator could be equal to 0. So 3 different vertical asymptotes. So we'd have a vertical asymptote at x equals 0, vertical asymptote at x equals 1, and vertical asymptote at x equals -4. Okay, so that's the process of looking for vertical asymptotes and also holes. We need to talk about horizontal asymptotes as well, because that's another part of the graph. So horizontal asymptotes, the graph will approach and get closer and closer and closer to horizontal asymptotes. We're going to look at 3 different situations, 3 different cases that happen to help us determine if there are horizontal asymptotes. So let's take a look. Some people prefer to memorize just the top heavy, equal degree, bottom heavy. And for me personally, I like to kind of think of one way or method to kind of think through the problem and not necessarily memorize what the answer is for top heavy, equal degree, and bottom heavy. So I'll kind of show you what I'm talking about here. If we have a situation where the numerator, the degree of the numerator, is greater than the degree of the denominator, then that's what's referred to as top heavy, because this degree is greater than this degree, which is understood to be 1. So in that particular situation, we'll look at what we get here, because what I'm going to ask or suggest that you do is think about compare leading coefficients, and we're going to do that for every situation. So this is how I like to think about it. So I want to compare the leading coefficients, but if I'm going to compare the leading coefficients, I need to be able to compare the same degree in both the numerator and the denominator. So if we're in the situation where we're top heavy and we have an x squared, even if it were x cubed, whatever, if the degree is higher, then we want to rewrite the denominator so that it has the same degree, but we need that placeholder. So I need to add a 0 x squared in here plus x. And now I want to compare these 2 numbers. I want to compare the leading coefficients of the same degree. So they have to be of the same degree. And I should add that in here. Let's do that. Compare leading coefficients of same degree. All right, so let's go back here to this situation. I've made my same degree by putting in a placeholder, and now I'm comparing 3 over 0. And if it's top heavy, in every case, when you do this, you're going to end up with some number over 0, because you'll have to add a 0 as a placeholder in the denominator. And if we have a number over 0, then we know that is undefined. So what that's telling us is that there is no horizontal asymptote. Okay, if there is equal degree, so we want to compare that same degree. If we have that same degree, then in this case, what we're doing is strictly comparing these leading coefficients. And that gives us our horizontal asymptote. So in this particular case, we would have y, sorry about that. In this particular solution, we would have y is equal to 3 over 4. But in general, we're going to be of the form where we compare those 2 numbers and we're some number over some number. So we're going to have some ratio. So what that's telling us is, as our horizontal asymptote, we're going to write this as y is equal to whatever that ratio is, that number over number. So as I said, in this particular case, it ends up being 3 over 4. Okay. The last situation we are looking at is if we are bottom heavy. And in that particular situation, that means the degree in the denominator is greater than the degree in the numerator. So we want to add a placeholder, so that means we need to add a 0x squared in this case. And now if we compare these leading coefficients, if you think about it, then in that case, if we're bottom heavy, it's always going to be of the form 0, all right, Ireland, 0 over some number. And we know that 0 over some number is equal to 0, and so what that's telling us is that the horizontal asymptote will be at y is equal to 0. So it's kind of up to you. For me, like I said, I prefer to just remember that I'm going to compare the leading coefficients in each case, and I have to remember to use placeholders if I need to. I think that's easiest because that's going to be the rule that I use for every situation, whereas others of you I know are going to want to just memorize. If it's top heavy, there's not a horizontal asymptote. If they're equal degree, you have to compare the leading coefficients. If it's bottom heavy, it's going to be y equals 0. Your choice. Let's look at some examples real quick and then we are done. All right. So it says find the horizontal asymptote. So that means we need to compare the degrees of the numerator and the denominator. And in this case, the degree is the same. So what that means is that we are looking at or considering the leading coefficients here. And so in that case, what that tells us is that our horizontal asymptote is going to be at y is equal to 9 over 3 or just 3. For the second case, if we compare the leading coefficients, the degree, we see that we need to fill in a placeholder of 0x squared. And now when we compare these leading coefficients, we find that we have y is equal to 0, because 0 over 3 is just 0. And then lastly, let's go back. Think about this in terms of what, if you're going to memorize this. This was bottom heavy, so it's going to be y equals 0. This had the same degree, equal degree, so it's going to be y equals that ratio. On this last one, if you notice, degree is higher here than it is here. So if we add this placeholder of 0x cubed, and we compare the ratio of this leading coefficient over this leading coefficient. If we're looking at 9 over 0, we know that's undefined. So that's telling us there is no horizontal asymptote. All right, we have learned kind of the basics to help us with actually graphing these polynomial functions.